So Dr. Oleg Pianykh received his master's from Lomonosov Moscow State University with honors in applied mathematics and physics, and his PhD in computer science from Louisiana State University. He's worked in industry as a CEO and as a consultant, and he serves as a visiting professor at the National Research University Higher School of Economics in Moscow, Russia, as well as a lecturer in medical informatics at Harvard University. He's currently the director of Medical Analytics Group in the Department of Radiology at the Massachusetts General Hospital and is an assistant professor at Harvard Medical School. He's been very actively working on developing and implementing data-driven healthcare applications for the past 20 years, with projects that have ranged from digital image analysis and most recently, clinical workflow optimization. He's also done a lot of teaching of graduate courses. He's authored several textbooks, including Digital Imaging and Communications in Medicine, DICOM, the DICOM standard, a practical introduction and survival guide, and Digital Image Quality in Medicine, which is part of the Understanding Medical Informatics series from Springer. His current interests include operations, management, machine learning, and data analyses in healthcare. And we've had a lot of our series talk about diagnostic tools using machine learning. We're going to hear something a little bit different from Dr. Pianykh, and we are delighted to have him here today. The title of his lecture is An Alternative to the Black Box, Strategy Learning. So let me stop sharing and give the screen to Dr. Pianykh.
Thank you very much, Dr. Andrew, for a nice introduction. Let me start sharing my screen. And I hope you can see it now. Is it on? Can you see my screen? Okay. Well, dear audience, thank you very much for finding the time to attend this class lecture.
And you may want to put it in projection mode, Oleg.
Oh, wait.
To
Am I showing the right one? Let me check. Let me double check. Hold on. Yeah, okay. I'm showing a different screen. That's why I was. How about now?
Perfect.
Okay, wonderful. Always confused by more than two screens. But we'll talk about it in this presentation today, about how many things humans can handle. So today, let's talk about a slightly different topic, which we have been developing for the past couple of years. Dr. Andrew introduced. I mean, we have a medical analytics group here at MGH, and basically our principal goal is to help with any real-life implementations using data science. And obviously, it involves a lot of machine learning exercises as well, building models and things like that. And I've done it a lot, and my team members have done it a lot as well. But at some point, you kind of try to think about what's beyond that. And if you look at current medical or even non-medical artificial intelligence, I would like to criticize it for a while, despite the fact, again, that we use it, we take advantage of that. It may be very instructive and very helpful in many cases. But if you think about the majority of models we are using right now, what we actually do is we take terabytes of data and transfer them into terabytes of coefficients. And either pile of data points or coefficient points is equally incomprehensible to us. So yeah, they can help us, and they build our neural networks and random forests and linear regressions, and they compute something, they predict something, they help. But one thing they do not seem to be doing is that they do not seem to advance our knowledge, our human knowledge, in any possible way. People definitely have been talking about interpretable and explainable AI for some time, but even in this case, we'll come back to that analogy a little bit later. It's an effort to understand the model rather than the effort of develop something which can easily fit in a human head. Let me give an example. For example, linear regression is often described as an interpretable model. And indeed, if you look at linear regression, you can understand, oh, well, this feature is multiplied by, by a pretty large coefficient, so it means something important. But can you use linear regression on a daily basis? Can you really multiply 5-digit numbers in your head? Likely not, right? Likely not. So you kind of understand the model, but still it remains pretty much not useful to you as a human being. It's not something you can use yourself on a daily basis. And the first time I ran into this obstacle a couple of years ago when the COVID came, and we really had to develop some even clinical models within very tight, short timelines. And that's when we understood that there is no way you can build the whole AI infrastructure in a couple of days, but you do need this knowledge. You do need to know how you can make the best possible decisions. So what do you do? How do you take advantage still of all this AI and computing power, but without converting gigabytes of data points into gigabytes of coefficients? So how can you establish this feedback loop? Because we use our knowledge to generate more data every day. That's what we do. But how do you go the other way around? How do you go from the knowledge, from data to the knowledge, back to the knowledge? And that's what humans used to do all their lives. That's how we practically acquire every bit of our knowledge. That's how the medicine was developed in, right? You experiment, you go by trial and error many times until you discover the best way of doing something. And then that's how you learn. But AI, in the way it's been done these days, is not the same as this intuitive process of humans becoming more and more knowledgeable about something. So how can we enhance that? And first of all, this problem comes in making decisions in healthcare in particular. We have to make decisions. We have to make diagnostic decisions. We have to make operational decisions all the time. And obviously, making decisions requires some kind of knowledge, requires some kind of conditions. You can look at any kind of healthcare decision process as a game theory exercise when you just playing a game. In a game theory sense, you may be playing this game against Mother Nature. You may be playing it against cancer, COVID, flu. You may be playing it against some kind of scheduling challenges, but you always seem to have some kind of opponent. And your chances to win depend on having a good strategy in your head, not in some kind of black box, not some kind of device, but because you have to do it on a daily basis, every single minute. You have to do it all the time. So you should have some strategy, which at least is good enough, somewhat rational, and definitely better than just flipping a coin. So which would increase your chances compared to random decision making, which still happens quite frequently, to be honest. Let's take an example. Let's take a simple, I guess, operational example. Imagine you need to schedule patients for examinations. I'm just using an operational example, but the subject is completely universal. And imagine the scenario: you have an MRI scan, you have to schedule 10 exams, and you know that out of those 10 exams, 5 exams are short and will take only half an hour, and the other 5 exams are long and they will require 60 minutes or 1 hour. But as it often happens in healthcare, you need to schedule them all into the same static 45-minute slots. You may scream at me at this point, say, it's insane. You cannot schedule 60 minutes into 45. But obviously we do it all the time. So let's accept the reality. And the goal in this game, in the simple scheduling game, is to reduce the overall patient wait time. How would you do that? How would you schedule those 5 short and 5 long exams? You cannot change the composition, but the only thing you can change is the order, right? So you have those 45-minute slots, you schedule exams in some order. L stands for long, 60 minutes. S stands for half an hour, short exam. And for example, okay, if I put my long exam first, it takes 60 minutes. By the end of this exam, I'm already late by 15 minutes. I'm delayed by 15 minutes. So my next exam, whether it's short or long, is going to start late. And my next patient will be waiting for 15 minutes. So what do? I mean, if I cannot change the duration of my examination, if I cannot change the composition of how many I have, the only way out is to change the sequencing, right? And if you think about it for a minute, you'll probably realize that if I want to minimize my overall delay, it does matter in what order I put those exams. For instance, if I put all long exams first, by the time I'm done with my 5 long exams, I will be terribly delayed, and my next patient is going to be terribly delayed. So probably this is not a good idea to begin with all long exams. Probably I need to do something else. Long story short, scheduling problems have been beaten to death in scientific literature and applications for decades. Many solvers had been proposed to solve those problems, from linear programming to neural networks, you name it. They're very different. They've been developed in different times using different algorithms. They share one thing in common. They're black boxes. They're complete black boxes, which means that not only do not understand how they arrive to a certain solution, but all they give to you is an instance of that solution. For example, if I run my problem through that black box, what it's going to produce, what's going to spit out is a sequence. It's going to tell me, if you go this way, LS, 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 your overall patient wait time is going to be minimal. And that's the optimal way to schedule in this particular instance. Well, great. I'm kind of left with that oracle, which gives me that solution, but it does not advance my knowledge in any possible way. Moreover, that solution is very fragile, because if anything happens tomorrow, if anything changes in my environment, I have to run again back to this oracle and ask him to give me the next optimal solution, and the next. And as we know, our operational and clinical environments change all the time. The exams on Sundays are different from exams on Fridays, and then the COVID comes with a huge disruption, and then something else happens, and things in July different from things in January, and data shifts, and so on. You cannot just function if you depend on this black box, which has to recompute the optimal instance, even if it's using the best possible algorithm, which is guaranteed to give you the best possible result. What you need instead, and what we frankly all use instead in our daily life, we do not use those instance solutions. They cannot even fit in our heads, right? If it gives me long strings of exams in whatever orders, I won't be even able to memorize it. What we use instead in our daily life is strategies. We use simple rules. And simple rules may be the ones you might see on my right hand of that slide. Maybe I need to alternate my long and short exams. Maybe I should just never put two long exams together. Maybe I should always start with a short exam. There may be different strategies. There may be different rules, but you kind of realize that it's much more practical to have the rules which we can use as humans, and which we can also easily compute in our heads, as opposed to being completely dependent on this black box oracle, which, by the way, also is pretty expensive, pretty hard to kind of set up, which requires a whole lot of maintenance and so on and so forth. So deploying artificial intelligence solution as we know it, whether it's transregression or neural network or anything like that, is a pretty heavy lifting exercise. It will take months in many cases. It will take data feeds from many systems which have to be orchestrated, connected, verified, done in real time, and so forth. It requires a lot of training and validation, and you name it, whether you solve any possible problem. So despite the fact that AI is very helpful, it definitely has very significant constraints, which become very limiting and very kind of serious in the cases when you have to act fast and when you have to be adaptive, because those solutions from a black box oracle, they just do not scale. They have to be changed all the time. And again, we cannot memorize them. So we do not want to be dependent on a black box. And frankly, in some areas, you cannot even be dependent on a black box at all, because you need to understand the logic of what's going on. So all that combined, and this critique of the AI as we know it now, kind of brings you to a natural idea. So why don't we approach it from a completely different angle? Why, instead of trying to learn optimal solutions, we instead try to discover the best optimal rules, which then we can use as the human beings, which can easily be memorized by us, which we can easily compute in our heads. So essentially, that's what I would call knowledge. Knowledge is something that humans used to develop by trial and error, but it's easily, again, computable by humans. We can easily modify it, we can easily share it, instead of, again, being dependent on this super optimal but very hard to manage solutions. How can we do that? Can we actually repurpose machine learning as we know it now into discovering those strategies which you can use instead? Well, let's go back to our scheduling example. Consider I'm a scheduler, right? I'm trying to schedule my next patient. Let's say I have already scheduled 4 exams, long, short, long, short. I'm trying to decide, should I schedule long exam next or should I schedule short exam next? So I'm sitting here in my game with a scheduling problem, and I'm trying to figure out what is the best possible decision, what strategy I can use to take the best possible move. I also, at this point, know something about my system, right? I know what exactly I scheduled. I know actually I can easily see if I'm still running behind or on time. I know that, for example, if I schedule 2 short exams and I have 5 in total, then it means I have 5. I have 3 exams left. So I know quite a few things. I'm just contemplating what is the next best move I can make in this game and how I can make it so that my chances to win, to come up in this case with the best, with the shortest wait time schedule, will be maximized. And again, the problem is completely generic. We are solving this problem in operations. We are solving this problem in diagnostics and clinical healthcare. We are solving this problem when we play in chess. I mean, the statement of this problem is completely universal. And it basically breaks in 2 pieces. First of all, you have to describe your current state using some kind of features. You have to develop the features we described. Okay, that's where I am right now. I scheduled 4 examinations. So this is probably my feature number 1. My feature number 2 may be, am I delayed after scheduling those 4 or not? That's probably my second feature. How many do I have left to schedule? That's probably my next feature, and so on. What happens is that humans are really bad with numbers. And the longer the numbers get, the worse we become. But humans are very good with simple logic. So we can ask ourselves questions, is it delayed or not? Or is this pediatric patient older than 18 years old or not? So they're very good with simple logic and simple thresholds. And by doing so, in my case, I can build those simple features. I can build the features which use simple logic, just like I described here. Okay, let's say I build my features. My features contain some numbers. My numbers describe my current situation with my scheduling. Obviously, the whole point right now is to decide what is the best move. Should I schedule my next exam as long, or should I schedule my next exam as short? And that's where the most intriguing point obviously comes, because I don't know. I don't know which one, which task I should be doing next. And that's where the machine computing power comes in play for the first time. So I want, for example, to determine for each one of those scenarios, what is the best move? What is the best decision I should be taking at this point to optimize my cost function, which may be patient wait time in this example. Well, what I can do is I can make my machine, let's say I'm assuming my next scheduled task is going to be task A, for example, short exam. Well, if I make this assumption, what I can do with my computer, I can simulate, I can play all possible branching, kind of all possible tails of that schedule. I can literally enumerate them approximately exactly. And overall, these possibilities, I can evaluate my cost. I can evaluate if my next task I scheduled was task A, what is the overall patient wait time in this scenario? I can do the same for task B. If I schedule my next task instead of task B, I can also use my computing power. It may be a lot of branching. It's not obvious to me at all. Actually, those problems have very high branching factors. So that's exactly where computers become extremely useful, because as a human, there is no way I can consider all possible tails of that schedule. There will be thousands and thousands of them. I cannot do that, but computers can sometimes do it in a split of a second. So I can delegate this task computer, and it will compute. Okay, if my next task is task B, then the patient cost, whatever wait time function is going to be different. And then I simply look at those two possibilities, and I pick the task, whether A or B, which will produce the best cost function in this particular case. So if I'm trying to minimize my patient wait time, I will pick the exam which I'm trying to schedule, which will result in a shorter wait time overall. That's it. That's how I'm using computing power to discover the best next decision I have to be making. Once this is done, I'm all set, because all I have to do right now is to simply make a table of all my features which describe where I'm right now in this game, how many I have scheduled, if I'm delayed or not, how many I have left, and so on and so forth. But for each possible set of features, for each possible combination on my game board, I already know what my best next move should be, whether it's A or B, whether it's a long exam, for example, or short exam. I do already know that, because that's what I have computed using, again, the extreme computing power of my computing device, which in this particular case goes much better compared to my human brain and can evaluate thousands of possible scenarios. But I end up with a simple classification problem then, when I have to come up with some way to map my features into my best outcome. And that's exactly where I bring the second tool in this game. So if before we used computers simply to pre-compute the best possible decision at each single step, now I want to discover the rules. I want to discover the rules which, if applied, will map my features into my best possible outcomes. For example, I want to know if I'm delayed, what should I schedule next? Or if I scheduled my long exam just now, and before I scheduled my short exam, which exam I should schedule next? Long story short, we have taken this approach. We have applied it to the problem I just described with 5 short exams, 5 long exams. We ran it, and it discovered from all possible features and all possible rules, the computer discovered a very simple thing. It discovered the logic which you can see here on the right-hand side. Again, from all possible features, and we had dozens of those features, and from all possible combinations of those features, how they can combined and merged together and used with different operators, it simply discovered that simple rule. If I'm delayed, I'm scheduling my next exam as my short exam. If I'm running on time, I can schedule my next exam as my long exam. That's it. So think about it for a second. We went through this exercise, and we used computing power at least twice. First of all, to evaluate the best possible move, and second, to discover this logic rule. But the result is so nice and so concise that I can simply, literally, put it in my head right now, and I can continue as a scheduler with that simple rule. And even if my environment changes, and I have to schedule 6 and 6 tomorrow or something like that, this rule will probably remain much more stable compared to that single instance solution, which really depends on the current layout of my environment, and which needs to be produced by a black box all the time, and I have to be taking trips to this black box all the time to get it done. So what I learned is a simple rule to win my game. I'm playing this game again against my all possible scheduling problems. So scheduling problems is kind of my opponent in this game. But I learned a simple strategy which significantly increases my chances to win. How exactly, we'll see in a second. And by being so simple, Again, I can understand it. It's completely interpretable. It makes perfect sense to me. It scales because if I have a different counts of exams, it will probably still apply. It's also very robust, and actually it's actionable. By actionable, I means I can take actions using that thing, because again, linear regression is interpretable, but linear regression is not actionable. I cannot compute linear regression in my head, at least efficiently. So we discovered a strategy. We discovered the optimal rule, which we can use. So essentially we learned. Because if I take a few steps back to that experiment with evaluating all possible branches, essentially computer in this case played this role of a human with kind of infinite buffer for trial and error. Computer was doing those countless, no, not completely countless, but thousands and millions of trial and error exercises for us to extract this best knowledge. That's what we used to do as humans without trial and error before. But now we completely delegated that to a machine, and machine became much more efficient in doing this trial and error compared to us. And that's how we achieve the goal. That's how, by delegating that to a computer, and also by delegating the rule discovery to a computer, we discovered a very simple and a very efficient rule, which again is much better compared to a black box in many, many ways. So that's what we end up with. Instead of a black box, which would give us just an instance of a best possible solution, we trained and we discovered a rule-based model, which is much more practical, no doubt, which in this case also happened to be very simple. Couple of examples. That's a little bit more advanced rule learning. In this case, we use a decision tree to learn the rules, but it may not be the only one. I mean, there are different flavors of rule models which simply learn the logic. Decision tree is I would say that's a subset of all possible models. So in this case, they actually learn two rules. Well, the first one is still if I'm currently delayed, yes or not. And the second one is actually if more than 50% of jobs have been already scheduled. So if I'm trying to schedule the second half of my schedule, and look what happens in this case, it tells me if I'm scheduling the second part of my day, I can schedule more long exams. This one takes some time to understand. But when you think about it, you realize that disrupting the early part of your schedule has a higher impact on the patient wait time compared to disrupting the second part of your day, which will not impact that many patients. So in the second half of your day, you have more flexibility with delays because they will not propagate into more patients. So that's a less intuitive, but one discovery. But once you see it, you kind of realize what happens. What you see on the right-hand side is essentially a histogram, which compares two things. You have minutes on this horizontal axis. So that's a patient wait time. And the blue histogram here with those 3 or even 4 humps corresponds to the random decision making. If I'm just scheduling the next task at random, which, believe me or not, happens sometimes. By random, I do not mean pejorative in any way. I simply mean we do not have any strategy. And quite frankly, and quite often, we do not have any strategy. And if we do not have any strategy, essentially we are forced to make random decisions. So blue corresponds to the random, and you see that with those bumps, well, my wait time may be easily 30, 45, even 60 minutes sometimes. But if I use that simple strategy, I have a sharp histogram, which is really about 15 to 20 minutes. Well, there is another way of half an hour, but you see how the whole distribution shifts into the shorter, much shorter wait times. And with a very high probability, I will be winning this scheduling game, despite the fact that I'm using a very simple rule, which again, I can easily evaluate in my head. I do not need a computer. I do not even need a calculator to ask myself, is it afternoon or is it morning, right? I know that. So I can easily use this rule, and this rule alone puts me already in a very privileged position of winning the scheduling game with extremely high probability compared to not using any rule at all. What also happens is that those rules, because they're so simple, tend to be extremely resistant to noise. And by noise, I understand all possible disruptions which may happen in real life. Let's say I assumed in the beginning that our exams are 30 minutes and 60 minutes, but obviously in real life, they will not be exactly 30 minutes and 60 minutes. So what we try to do here, we added random noise to the duration of our exams. And we went as far as adding 100% random noise to the duration of our exams. Basically, at that point, you cannot, as a human, even differentiate between long and short. The exam durations became so noisy that as a human, you cannot even know what's going on. Yet, if that 50% line corresponds to the random decision, those lines correspond to different strategies we built with those simple rules. And you see, yes, the quality of decision-making goes down, obviously, as we keep adding more noise. Let's say if it was, I guess, around 95% quality at a no noise case, then at, I don't know, at 50, we're down to maybe 65, 70% of winning. But even when we get to 100% noise, we are 60% and above. So we are pretty much still winning the game. When the whole environment becomes essentially completely noisy, somehow miraculously, those rules, because they're so simple, they do not overfit, and they extract the very essence of what's going on, they turn out to be very persistent and very reliable and very robust compared to the more complicated models, which will definitely fall apart at this point. More complex models will definitely fall apart at that point. Also, what we discovered in this particular instance, when we compared our models to classical AI, let's just look at a couple of examples. This is what we used. Ignoring the titles for a second. That's the model we used to extract this logic. We call it exhaustive tree because it was trying to build all possible combinations of splits. And you see that 93% for, and those different problems, slightly different scheduling problems, P1, P2, P3. The bottom line is this model was performing pretty well. It was winning compared to random in 93, 95, 91% of cases. When we go to random forest, classical AI, sometimes the performance is the same, sometimes actually it gets significantly worse, 85% compared to 91. So what happens to even to my kind of utmost surprise, is that we see that in many problems, clinical, operational, some other problems, those simple rule models can actually compete in their quality with the black boxes. But again, the principal difference is that the rule model, you can easily remember, you can easily evaluate yourself, you can easily share it with a whole bunch of other humans. So it really becomes knowledge. It becomes a simple piece of human knowledge, which travels in our humanity, in our society, as any knowledge would do. While random forest is a complete black box. You cannot understand it. You cannot share it. You cannot modify it. You cannot do anything about it. So that's how we arrived to what essentially the plan was. We can establish that feedback. We actually can, using rule models, develop this complete this loop and go from all the data we generate back to some human knowledge. Let me now give you a few more details about how exactly that happened. That's kind of the second part of the presentation. So what did we do? So what exactly I define as human knowledge? It's kind of understandable intuitively that we can only do simple logic and we can only do some features. But what helped us in this particular case, excuse me, is that there's been a fair amount of research in psychology on what the humans can process efficiently. And that's exactly the papers I went to when I started thinking about it for the first time. And when you go through those papers, you'll discover that it's pretty much established that humans in their decision making can use only up to 4 features, for example. That's why I was confused between my two screens, maybe. In my case, it's two. Really, if you think even about what you do in your daily experience, think about it, right? Whether you decide if you should go if you should go out today, or if you should take this class, or I don't know, if you should cook anything for your dinner. You probably use at most up to 4, if not less, features to make that decision. The same actually happens in healthcare as well. There may be tons of them, but only up to 4 will be the most decisive, which will drive your decision. And those up to 4 features are usually connected with up to 4 operators, by which I mean just simple and, or, not, and actually some. Some is another operator, which basically means I say, okay, if out of 3 conditions, 2 are satisfied, then I'm going to do that. Any 2. I'm not concerned with specifically which ones. So what I'm driving is that psychology pretty much describes what humans can compute efficiently. And that's what exactly drove our kind of development of those human knowledge models in our case. So instead of interpretable, explainable, which people used to do in AI, and actually nobody even explained ever to any one of us what interpretable means. There's no definition of that. What I'm saying is that we can actually use psychology research, and we can reasonably define what human knowledge model should look like, what it should include, how complex it should be. And that brings us to something which has 2 principal components. On one side, we have math, pure math, which has the concept of rule learning models. So in mathematics, you can develop models to discover rules. I'm not going deeper in that exercise. It's a pretty complex thing. It's actually exponentially complex. And as we add more and more variables to those models, the time to discover those models will essentially explode exponentially. They're very expensive. That's why people used to stay away from those models all the time. They say, no, it's too complex, it's too exponential, we don't want to touch that. However, what we have on the other side is humans. And humans put those significant limitations on the complexity of those models. For example, if I say that it's only 4 variables, it significantly reduces my search space. And by doing so, what happens when I bring those humans on one side and math on the other side together, I end up with something which I can actually compute in a reasonably short time. So what I'm saying is that I can discover those human knowledge models, despite the fact that they're exponential, simply by using those constraints from psychology. I can discover those models pretty fast. And I can create, similar to classical AI models, I can create my human knowledge learning model. And I can train this model just like I train anything else. So to conclude, a couple of examples. Example number 1, human knowledge models which try for COVID data set, predicting if the patient is going to end up in ICU. So that's a funny chart. It's built in 2 principal dimensions, precision and recall. So the closer you get to that corner, the more accurate your model becomes. What you can see here, we tried human knowledge learning models of size 1, and they created this funny diagonal pattern, but they were not very predictive. But we went to size 2, to size 3, and to size 4. By size, I understand the number of features, right? We can afford up to 4 for the human thinking. When we made it up to size 4, those black crosses correspond to my black box XGBoost random forest model trained. You see that the quality of those models overlapped with the quality of the black box, essentially. They touched and they kind of overlapped the black box. So they produce the same quality of classification as the black box, but with, again, the same principal distinction. The black box was a black box, which would give us solutions for instances, right? A prediction instance for each patient. Okay, this patient is going to end up in ICU. This patient is not going to end up in ICU. Why? Nobody knows. It's a black box. While the human knowledge learning models produce the rules, which I can look at, I can read, I can understand, and I can use myself as a physician, for instance, to simply decide if that patient is at high risk of going to the ICU. Simple as that. I do not need any servers, data feeds, nothing. I simply run it in my head. Conclusions. I mentioned that we started with that experiment in 2020 when we had kind of very high pressure to develop some models for our ED department and some other models as well. And we did not have time, and we definitely did not have time to build any black boxes and to establish any kind of IT data feeds into those black boxes as well. So that's another model. And actually, you can look at some of the rules the model discovered. It was very similar to the previous one. It was discovering the risk of a patient to end up on high oxygen in 48 hours. ED patient being on high oxygen within 48 hours. And the model learned some rules. You can literally read those rules if whatever oxygen saturation is less than that or has leukemia and da. So that's kind of the rules the model has discovered. And discovered quite a few. And discovered those best rules in 2.5 days, which I was running this model on a pretty high-end computer. It took the whole weekend essentially to run this model. It tried 10 billion different combinations of those features and rules and thresholds to discover the best ones on top. Fine, but after that weekend, after those 2.5 days, I had them all on top. And frankly, the accuracy was remarkable. It was 70% for something that simple, that short, I mean, as a rule. And what happened after, when I started reading all these rules, so that was done in April, May 2020. I started looking at those features and say, okay, well, I understand saturation, oxygen saturation has to be high, right, to rule it out. Or So some of those were making sense to me, but some I just, and again, I don't have clinical background. Like, what is connective tissue disorder, right? Why that has to do anything with COVID? What happened after, however, is that when I checked a few months later, I simply Googled. I went to PubMed. I went to some other publications. A few months later, the papers came out, demonstrated that, yes, leukemia is a high risk factor. Yes, connective tissue disorder is a high risk factor. Yes, heart rate, increased heart rate is a high risk factor, and so on and so forth. The papers came out after half a year or more on each one of those features discovered by the model in April 2020, confirming that that's indeed the case. So that's precisely the point I'm trying to make. By delegating this search, this trial and error, in essence, to a machine, which is much more computationally extensive compared to humans, we're taking a huge shortcut in our human knowledge development. We are not going by a classical trial and error, which is so time-consuming, which is so risky, in which we frankly can cost lives in healthcare. We take an enormous shortcut, and in 2 days, we might discover something which will take months and years otherwise, simply because the computer can play back so many possible scenarios, and from those scenarios, it can extract the rules which guarantee the best strategies or the best predictions of something. And that's what actually we kind of end up with. So instead of using black boxes, we have this nice opportunity right now, as I can see it, to learn actually human knowledge. And by human knowledge, again, understand something which we can use actively, proactively, to make decisions, to make them on the fly, even to understand and to modify those decisions because we understand them. They're very natural to us. Those models produce the rules which are very organic to the way we think. And most of all, they advance us as humanity because they give us a better understanding of what's going on around us. That's all. That's the end of my talk. Thank you very much.
Thank you very much, Dr. Pianykh. That was fascinating. Really interesting. Where your goal here has really been to to use machine learning and the computational powers to come up with a strategy by understanding which features are most important. And it sounds a little bit to me like it's a combination of classical machine learning, where when we were doing image analysis applications, computer-aided detection types of tools, an example would be in breast imaging, we kind of handcrafted the features of what we thought were important and used those. Do you see this kind of methodology being beneficial perhaps to combine with the other approach, or is it something that you see stands on its own? I mean, I guess, what if we don't know, what if we can't determine the features for a particular problem?
Yeah, I agree. Well, first of all, the benefit of this approach is that your target is a small model, which has, for example, up to 4 features. But in the very beginning, you may have as many as you want. I may start with a data set which has 100 features, and I can add some additional feature engineering tools to even multiply this initial number of features. For example, I can take different possible interactions between my features, right? And then, but still, after that, I will run this model to narrow it down to the best 4 feature combinations. So let's say out of 100 possible features and out of billions of ways to pick 4 out of the 100, it will find the best 4, which when combined, give me the best possible prediction. So that in a sense already works as feature engineering, because it extracts the best from this whole data set. Can you put anything on top of that? Yeah, I think that would be next step, because you can use some kind of automated feature engineering approaches, which will create more features on the fly to be considered. And what also, speaking of the imaging piece, I think it would be interesting to try it even with the images, because obviously the images are different. The examples I gave you used numerical and textual data, right? I was not using pixels in any way, but I bet we can try to tackle convolutions as well. I bet it may discover something like if you have a dark spot in this area, or if you have a certain shape in that area, or if your boundary looks like something. I bet it may try to do something like that, which again will speak to radiology minds in a much more human and interpretable way.
No, that's great. We have a number of questions in the chat box here, and you were just talking about the pixel data, and these operational problems are extremely important. We're very inefficient in medicine, and if we can use these techniques to improve operational workflow and so on to be more efficient and reduce wait times and so on, so very important. But one of the questions here is, how would you put a more complex problems with more features like image analysis into this scheme, and which features would you use? How would you approach a problem like that?
Well, obviously it takes some domain knowledge, right? It cannot invent features on its own. What it really does is that if it has a large number of features, it will produce the best combination of 4, maybe, or 3, to come up with the best possible result. But building the features, it may be automated, but in the best case scenario, it will take it will require some domain knowledge. So it's a combination. You essentially sit down and you try to, at the very first step, you, even yourself, you're trying to invent as many features as possible, even in the imaging domain. In the imaging domain, if you take neural networks, some of those features may be convolutions, but some of those convolutions could be interpretable, I think, because they try to detect certain shapes, for instance, which we can understand what they're looking for. So, long story short, I have not tried the images yet. I would love to do it as a next step. That's what I'm thinking about. But the approach would be to take as many features from the domain knowledge and then try to also develop, when you're down to 3 or 4, even convolutions, you can probably look at those 3 convolutions and try to understand what they mean. That's already possible. That's what you may try to understand as a human. You cannot look at all possible convolutions. You cannot look at 10 or 12 or 50 or 1,000 convolutions. But if it discovers the best, that's when it can feed back probably to your domain knowledge. And probably you might be able to understand what it's trying to tell you. It's a little bit more challenging, I agree, in the imaging domain, but I don't think it's desperate at all.
Great. And so a couple of other questions here. One is, if tables become big enough, where is the difference to linear regression? So if a human can't perform that lookup table in their head either, so we would end up in a situation comparable to the linear regression model. So I guess they're asking, I guess they're asking the details around a more complex problem where maybe there aren't 4 features that can define something. And it really takes more than 4 features for us to understand, for the problem to understand. Then the tables are going to get quite large, are they not?
Okay, well, that's easy to address. I mean, there are definitely problems which will take more than 4 features. Definitely, no doubt. I seriously doubt that you can play and win chess using only 4 features. No, it's not going to happen. But what I'm saying is that, and what I have seen myself in many examples, that in many problems that we tackle in our clinical and operational kind of healthcare exercises, it seems to be sufficient. It probably looks so that the problems which originate from human experiences tend to be low dimensional. We do not seem to create problems with huge branching factors as you have in chess. It actually happens quite frequently. In addition to that, okay, let's say we need at least 10 features to understand something. All I'm saying in this case, if I give you 4, you will not be able to remember 10. But if you know 4, and if those 4 still get you above the no-knowledge level, let's say they get you only to 50% ahead of knowing nothing, it's still a huge step forward. And it's something that you can accomplish yourself again without using any black box.
Interesting. Interesting. We have kind of a theoretical question here, or
Okay.
maybe a contrarian question from Dr. Chris Bridge, whom you probably know.
Yeah, Chris. Hi.
He asks, do you think that interpretable, the form of what we're calling interpretable AI, is this synonymous with something that a human can perform themselves, or is one a lower bar than the other? So is interpretable and what a human being can do, are those synonymous, or is there a ranking there?
I don't like interpretable, first of all, because nobody frankly defined it. I have not seen a pretty good definition of what it means. While in what I explained to you, we try to use psychology and order discovery to come up with the specific constraints on what the models should be. Interpretable is completely loosely defined. And I gave an example of regression, linear regression. A lot of people call it interpretable, but it's not. Because, well, let me give another example. Let's say you have a linear regression, and to predict something, it takes half of patient's weight and 3 times patient's temperature, right? Well, it's a simple linear regression. It has only 2 features in it. But if you add pounds to degrees Fahrenheit, what is that? Is it interpretable? It makes no physical sense. Regression is not interpretable, at least by the means of our physical world around us. Neither it is computable, because if your coefficient in linear regression is 7.123 and you have to multiply it by 98.5 degrees of a patient temperature, okay, go ahead, do it all. I mean, it will take you some effort. You will need probably at least a piece of paper to do that. So it's not something which is easy to use in a daily life either. So I think that's a good example of something probably originating with a very confusing definition of what interpretable is. What I was talking about stands above, because I add additional constraints. I'm saying, no, I don't want that to be just interpretable. I want it to be computable by the humans, computable efficiently, so that number one, I can memorize enough features, and that's 4. And number 2, I can use very basic operators such as Boolean logic.
And interesting. And as you know, some of the quote unquote interpretable techniques that people are using, at least on the pixel side of things, looking at attention maps and saliency maps and so on, can have different consequences and an understanding of what's happening. So, and we've seen some questions about whether those techniques are actually useful and correct. I wish we could talk more. This has been fantastic. We've had some wonderful questions. This was a great talk, Dr. Pianykh. Thank you so very much. And we will wrap up this session, and next month we will have Dr. Ziad Obermeyer, who always has some controversial things and interesting things to say. But Dr. Pianykh, thank you so very much for this wonderful session. Thank you.
Thank you very much for inviting me. Thank you.